Hi, we are Team 17, and our project is about entropy-optimal sorting for random shuffle sequences with short-change robustness. So in the film industry, sometimes there might be situations where movie assets are out of order, such as when file names for movie frames are accidentally mixed up. We can actually restore the corrupted data by sorting, which is a primary motivation for our problem. So our project focuses on supervised sorting of randomized frame sequences. So our task is to design a supervised model for sorting sequence of anime images for Japanese anime film Kimi no Na wa. So this is a multi-class classification task where the input is a randomly ordered image sequence and the output is a class label, which actually represents the order sequence. So for a data set, we will be using Kimi no Na wa, as I mentioned before. And here's how we will pre-process our data set. So we first split the entire film into various shots. And to construct an input sequence from our model, we randomly pick 4 frames from shot 1 and pick the first frame from shot 2, and we shuffle its order. So this is what we call 4+1 input configuration, with 4 frames from the first shot and 1 frame from the second shot. We will also be using other input sequence configurations in our experiments. So the reason why we include a frame from a separate shot is because we want to evaluate the model robustness to shot change. Here is our proposed approach. So the overall architecture of our network is composed of a CNN, which is used for feature extraction, and a multi-layer perceptron that maps CNN output to predicted order. The novel aspect of our architecture is that for a CNN module, instead of passing the images in the input sequence one by one to the CNN, we stack all the input image channels together and treat it as one single input and pass it to the CNN. So here are the input sequence configurations tested in our experiments from 1+1 to 5+1. So to evaluate our proposed approach, we have a baseline approach. For the baseline approach, it also uses a similar architecture as our proposed approach. The main difference being that for the CNN module, we pass the individual frames in the input sequence one by one to the CNN, and this is achieved by slicing the channels corresponding to each image. And to conduct feature extraction, we implemented and tested 3 CNN models, ResNet, EfficientNet, and RegNet. And here are a list of the data augmentation methods that we explored, as well as the hyperparameters that are used during training for all of our models. And for evaluation, we will be using accuracy and another self-defined metric called accuracy growth factor, AGF, which is the ratio between prediction and random guess accuracy. This table shows the random guess accuracy for different input sequence configurations. And here are the results for the baseline approach. So we can see from this table that the AGF values are actually quite low across all input configurations and models. Whereas here's the results for the proposed approach. So we can see that the AGF values are significantly higher than the baseline. And especially for 5+1 input configuration with EfficientNet, it is actually 152 times more accurate than random guessing. Furthermore, as shown from this plot, the proposed approach achieves higher AGF across all CNN models and input configurations compared to baseline approach. We believe our approach outperforms baseline approach because stacking the channels preserves the context of the input sequence on a higher level, which is critical for sorting tasks. And here are the results for the data augmentation. So here we first define an additional metric called shot detection accuracy, which is the accuracy of predicting the frame from the second shot as the last frame in the sequence. So we are doing so to see whether our model is robust to significant changes in frames. We find that random crop plus horizontal flip results in best performance for both sorting and shot detection. And we also find that using this technique results in 30% accuracy in sorting and 97% in shot detection. So this indicates that our models are having difficulty with ordering images with minor perturbation, primarily due to the difficulty and the challenge of this task, but are actually quite successful with ordering images with significant changes. In conclusion, we find that our proposed approach, which simply stacks all input channels together and treating the entire sequence as a single input, significantly outperforms the baseline approach across models and input configurations. We find that the CNN models achieve comparable performances, while random crop with random horizontal flip help improve model performance the most. Lastly, we find that our model is quite robust to shot change. And finally, for our future work, we would like to potentially incorporate more animes to construct a more diverse training set, investigate pairwise prediction approach, and also explore motion regions to decrease the computational cost of our work. And that's it for our project. Thanks for listening.